Okay, so get this. We are now at a point where we've actually photographed not one, but two of these things. These objects, so dense, it's such intense gravity that light itself can't escape. I mean, think about that for a second. For centuries, black holes were just this theoretical idea, right? Something you'd scribble on a chalkboard. And now, we've got pictures.
It's definitely a perspective shift. I mean, these were once purely theoretical objects, almost like these, mythical beasts of the cosmos. And now these images give us a tangible way to connect with this extreme physics that's happening out there.
Absolutely. And that actually brings us to you, dear listener. We've gotten a ton of questions about black holes lately and all the progress that's been made. So, we're going to take a deep dive into this crazy, fascinating world of black holes. And today, we're really going to try to grasp what's going on with these things. Especially what happens to all the stuff that falls into them.
Yeah, that question has definitely been keeping physicists up at night for decades. We'll get into how we even study these things when we can't actually see them. And those incredible photos, we'll talk about the insights they've given us. And of course, we can't forget about some of the revolutionary ideas that are still, being hotly debated in the scientific community.
So how do you even begin to study something that is fundamentally invisible?
Yeah.
And you can't just point your telescope at it, right?
Yeah, exactly. For a long time, our understanding was based almost entirely on theoretical work, stemming from Einstein's theory of general relativity. But things really changed with direct observation, through two key avenues.
You're talking about those amazing photos, right? The ones that basically broke the internet. Tell us a little bit more about what those images actually show us.
Well, we actually have two landmark images now. The first one, from the Event Horizon Telescope, it captured the supermassive black hole at the center of the galaxy M87. Now, this thing is a staggering 55 million light years away. It's got a mass about 6 billion times that of our sun. And then we have the image of Sagittarius A star. That's the black hole at the center of our own Milky Way galaxy. And that one's, comparatively smaller. It's only about 6 million times the mass of our sun.
Okay, 6 million suns hardly sounds small to me. And I remember when that M87 image came out, the sheer scale of it was just mind-boggling. 6 billion suns. Is that even close to the biggest black hole that we know about out there?
Not the absolute largest, no. There are some other candidates out there that could be even more massive. But the M87 black hole, it really serves as a great example of the scale we're dealing with here. To understand the density, just think about our own sun. If you could somehow compress it down into a black hole, its event horizon, which is basically the point of no return, would have a radius of only about 3 kilometers. So our sun, which could fit over 1 million Earths inside, squeezed down to just 2 miles across.
Wow. Okay, so a black hole with 6 billion times the mass of the sun. Its event horizon must be on a completely different scale.
Oh, for sure. It would be bigger than our entire solar system. And these photographs, which, by the way, are a phenomenal feat of engineering, they were only possible by linking together a whole network of radio telescopes. They were spread across the globe, basically creating one giant virtual telescope the size of the Earth.
That's right. It was like collecting data from all these different spots and then piecing it all together. It's like, I don't know, trying to see a grain of sand on the moon. But instead of visible light, they're using radio waves.
It really is astounding technology. And then in addition to these photos, we have another incredibly powerful tool, the detection of gravitational waves.
Ah, yes. Those ripples in the fabric of space-time. It's like something out of science fiction, so we can actually measure those.
Isn't it? These waves are created by some of the most, cataclysmic events in the cosmos. Things like two black holes spiraling into each other and then merging. So you have these incredibly massive objects. They dance closer and closer, and when they finally collide, boom, they send out these ripples through space-time.
I remember Kip Thorne, who's, a pioneer in the field and a Nobel laureate. He described it as a storm in time. That's always stuck with me. So these events that happened millions, even billions of light years away, they're actually causing tiny distortions here on Earth right now.
That's exactly it. The effect is tiny, really tiny, but the instruments we have are super sensitive. The Laser Interferometer Gravitational Wave Observatory, or LIGO, uses these laser beams that travel down 4-kilometer-long arms, and those lasers, they can detect changes in the length of those arms that are smaller than the diameter of an atomic nucleus, and those changes are caused by those passing gravitational waves.
Smaller than the diameter of an atomic nucleus. That is just incredibly sensitive. So these massive cosmic mergers that happened, I don't know, eons ago in some distant galaxy, they're actually rippling through our present moment. Pretty humbling to think about, actually.
It really is. Now let's go back to those photographs, especially the one of the M87 black hole. What exactly are we looking at when we see that bright orange ring?
Well, from what I understand, that bright ring isn't actually the black hole itself, because nothing, not even light, can escape its gravity once it crosses the event horizon, right? So we're actually seeing light from the superheated matter swirling around the black hole, and that's what's called the accretion disk.
Exactly right. Think of it like water circling a drain, and it's moving really fast. The friction within this disk, the material rubbing against itself as it gets pulled inward, it creates a ton of heat. And that causes it to glow intensely across a bunch of different wavelengths, including the radio waves that the Event Horizon Telescope was designed to observe. And it's really flat, much like the rings around Saturn.
And what's really striking about the image is that dark region in the center. It's often called the shadow of the black hole. And it's surrounded by that bright ring. But there's more to that ring than just hot gas, right?
Absolutely. The gravity of the black hole is so strong that it bends the path of the light coming from that accretion disk. Some of the light that would normally just travel away from us is bent around the black hole. So we actually see light from the far side of the disk, but it's all distorted and warped by that intense gravity.
So we're not just looking at a flat disk edge on. The gravity's acting like a lens, almost giving us a wraparound view of the material swirling around the black hole.
Exactly. And you know what? The size and shape of that shadow, that dark central region, it matches perfectly with the predictions from Einstein's theory of general relativity, which he developed in 1915. Talk about a confirmation of his work.
It really is phenomenal. A theory from over a century ago predicting exactly what we would observe using this incredibly advanced technology.
There you go.
Okay, so we're studying black holes through theories, through these amazing photographs, and by detecting those ripples, those gravitational waves from their collisions. But it all comes back to the fundamental question you brought up at the beginning. What happens to all the stuff that falls in? And this is where the work of Stephen Hawking really comes into play, right?
It does. In the 1970s, Hawking decided to tackle this question, and his work led to a really revolutionary discovery, Hawking radiation.
Okay, so let's break this down. A black hole, radiating energy. That seems to go against the whole definition of a black hole, that nothing, not even light, can escape.
It does seem that way, right? But Hawking showed us through a combination of general relativity and quantum mechanics that black holes aren't actually completely black. So because of quantum effects happening near the event horizon, black holes emit a faint glow. It's almost as if they have a temperature. Although for stellar mass black holes, this temperature is unbelievably low.
So they're not just these cosmic vacuum cleaners sucking up everything in sight. They're actually giving something back, even if it's super tiny.
In a way, yes, they emit this radiation, this Hawking radiation, and it carries away energy. And because energy and mass are equivalent, remember Einstein's famous equation, E equals mc squared, as they lose energy, they also lose mass. This means that black holes aren't eternal. They have a lifespan. They'll eventually evaporate completely, but it takes an incredibly long time. For a black hole the mass of our sun, it would take far, far longer than the current age of the universe. But for smaller black holes, this evaporation could actually be more significant, on cosmological timescales. So what does this mean? It means that black holes, these seemingly eternal objects, are actually slowly dissolving over time. It changes how we think about the ultimate fate of matter in the universe.
That is mind-blowing. Black holes, these invincible objects, are actually fading away. It's kind of poetic in a weird cosmic way. And it shows how important this discovery was, because that equation, the one for black hole temperature, it's inscribed on Hawking's memorial stone in Westminster Abbey, right alongside names like Newton and Shakespeare. That's pretty good company.
It really shows the impact of this idea. However, Hawking's calculation also led to something known as the black hole information paradox. And it's a pretty fundamental challenge to how we understand the universe.
Okay, now it gets really interesting. The paradox. So if black holes eventually disappear because of Hawking radiation, what happens to all the stuff, all the information that fell into them in the first place?
Exactly. Hawking's calculations, they suggested that the Hawking radiation doesn't actually contain any information about what went into the black hole. It seemed to be just thermal radiation, determined only by the black hole's temperature, and not by the specifics of the matter that it had swallowed.
And why is that such a problem for physicists?
Because it goes against a really fundamental principle in physics. Information is never truly destroyed. It might get all scrambled up, or it might be super hard to retrieve, but it's always there. It's encoded in the states of the particles.
It's like that analogy used before with the notepad and the pen. Even if you burn it to ashes, in theory, All the information, the ink, the paper, the patterns of the flames, it's all still there. It's encoded in those resulting particles and radiation. It's just super complex to decode. Now, when physicists talk about information in this context, they're not just talking about the words on a page. They mean a complete description down to the tiniest details of all the particles that make up something. And the laws of physics say that this information can never truly vanish.
Exactly. The laws of physics as we know them, outside of black holes, they suggest that information is never lost. But Hawking's calculation, it seemed to point to black holes as this weird exception, a place where information could be totally erased.
So the radiation coming out seemed to be completely independent of what crossed the event horizon, what went towards the singularity.
That's the heart of the paradox. It's like the black hole is this blank slate, and the radiation it emits is always the same, no matter what it's eaten or what its history is.
And just so everyone's clear, the event horizon is that point of no return, right? Once you cross it, you can't come back. Not even light.
Right. It's the boundary where the gravity is so strong that the escape velocity, the speed you'd need to escape, is faster than the speed of light. And it's interesting to think about, what if you were to fall into a supermassive black hole, like the one in M87? You wouldn't actually notice anything too strange right away. You'd just keep falling. The massive difference in mass between these supermassive black holes and, say, smaller stellar black holes also impacts things like tidal forces. The difference in gravitational pull between different parts of your body. So for a supermassive black hole, the tidal forces at the horizon would be pretty gentle.
So no getting ripped apart at the boundary for a really big black hole.
Not at the horizon, no. The real trouble starts later, as you're pulled towards the singularity at the very center.
That singularity, that mysterious point at the heart of a black hole. Einstein's theory describes it in a pretty extreme way, right?
Yeah, it does. According to general relativity, the singularity is where space and time become infinitely distorted. The density goes to infinity, and the laws of physics, as we know them, they just break down. Some physicists actually find it helpful to think of the singularity not as a point, but as a boundary, like the end of time itself for anything that falls in. Think of it like this. Once you cross that event horizon, all your possible future paths in space-time lead to that singularity. You can't escape it any more than you can escape tomorrow. Time, in a sense, just stops having a future beyond that point.
So it's like trying to outrun the next day, right?
Yeah.
You're inevitably heading towards it. So back to the information paradox, this Hawking radiation that's supposedly empty of information, it's coming from this event horizon, this point of no return. And the actual stuff that has the information, it's heading toward this end of time singularity. They seem completely disconnected.
And that's exactly the issue. The Hawking radiation seems to be generated by these quantum fluctuations in the vacuum of space. And they're happening right at the event horizon. It's almost as if the gravity is pulling virtual particles into real existence. And this process, it seems to be completely random. It doesn't depend on the specific stuff that fell into the black hole.
So we've got Einstein's theory, which is super elegant and gives us this framework for understanding black holes. It predicted their existence and even their appearance, which was confirmed by these observations. But then we've got Hawking's work, which suggests that they radiate and eventually vanish. But in doing so, they seem to break one of the most fundamental rules of physics by destroying information. It's like these two pillars of modern physics are clashing when it comes to black holes. So we've gone from first theorizing about these things to actually seeing them, and now we're dealing with the really deep implications of their existence and their eventual disappearance.
That's a great way to put it. While Einstein's theory is great at describing gravity and the large-scale structure of space-time, it doesn't fully incorporate quantum mechanics, the theory that governs the world of particles. So it's widely believed that to fully understand black holes and to solve the information paradox, we need a theory that can merge quantum mechanics and gravity. And physicists are actively working on that.
So even though we've made these incredible leaps forward, we're still left with this really profound and puzzling mystery at the heart of it all. We've learned a lot, but there's still so much we don't know. And Hawking's calculation, while groundbreaking, has opened up this fundamental question that scientists are still grappling with today.
It has. The fact that his calculation suggested there's no information in the radiation, that it's somehow separate from the stuff falling in and originates from the horizon, it's a big focus of current research. It shows how deeply connected gravity, quantum mechanics, and the nature of information itself really are.
So to wrap up our deep dive, we've gone from the unbelievable fact that we can now take pictures of these massive objects that trap light to the equally mind-blowing idea that they radiate and fade away over time. And right at the center of it all is this huge question. What actually happens to the information of everything that falls past that point of no return?
We've talked about how direct observations, those incredible photos, and the detection of gravitational waves, they're giving us unprecedented insights into these objects, and they're confirming Einstein's theories in stunning ways. But Stephen Hawking's work has revealed this really deep inconsistency in our current understanding of the universe. And it's forcing us to confront fundamental questions about information, about the nature of reality itself at these extremes.
And it's still so surprising, right? These objects that seem so absolute, so final, they're actually the source of some of the deepest ongoing mysteries in science.
Absolutely. They're at the forefront of our quest to figure out the universe's secrets.
So for you, our listener, we'll leave you with this thought. What if information truly could be lost from the universe? What would that mean for our understanding of reality? How would it change how we think about time and causality? Because as fascinating as this deep dive has been, it really just scratches the surface of this mind-bending topic. There's a whole universe of questions still out there, and maybe you'll be the one to help answer them.